Hello all, welcome back to our discussion on atmospheric waves. Today we'll be discussing yet another example of wave-like motion that appears in the tropics, so-called mixed Rossby-gravity waves. Mixed Rossby-gravity waves are an example of trapped waves. We've already seen two examples of trapped waves in the form of coastal Kelvin waves and equatorial Kelvin waves. These are waves which basically decay exponentially away from a boundary, such as the equator or a coastline. Trapped waves include equatorial and coastal Kelvin waves, equatorial Rossby waves, mixed Rossby-gravity waves, and equatorial inertia gravity waves. This lecture will focus on the last three in the list. So let's look at the derivation for these type of waves. We're going to start with the shallow water equations again with no topography, and we're going to have a Coriolis parameter approximated by an equatorial beta plane. That is, we're going to assume that f naught is equal to 0, as one would expect around a reference latitude of phi equals 0, and we're further going to assume that the beta parameter is simply given by 2 omega over a. The result is that the Coriolis parameter f is 2 omega over a times y. Substituting this into the shallow water equations then gives the form shown below. We linearize the shallow water equations about a state of rest with mean height capital H. Here the quantity phi is a geopotential quantity given by g times h. And by making this substitution, we then obtain equations 1, 2, and 3 here, again obtained via linearization. That is, we assume that capital H has no derivative quantities associated with it. All derivatives are equal to 0, and we assume that any product of prime quantities is small and hence can be neglected. Now we're going to seek wave-like solutions of this, which vary in the meridional direction, but are wave-like in the zonal direction. So this procedure is again very much analogous to our approach for equatorial Kelvin waves. This yields a system of equations shown here, equations 1, 2, and 3. In particular, note that we still obtain derivatives of, with respect to y, of both the geopotential phi hat and the meridional velocity v. The difference between this derivation and that for equatorial Kelvin waves is here we have made no assumption of 0 meridional velocity. We can now solve equation 1 for u hat and then use that in equations 2 and 3 in order to eliminate u hat from the system of equations. We then solve equation number 6 for phi hat, obtaining equation number 7 shown here, which will allow us to eliminate phi hat from equation number 5. However, observe closely that in order to make this substitution, we've had to divide through by nu squared minus GHK squared. This will come up later as one of the solutions that will actually arise from the derivation sets this term equal to 0, and hence would disobey the criteria, or hence would prevent us from dividing through by it in equation number 6. If we plug equation number 7 into equation number 5, that then gives us a second order differential equation for the amplitude function of the meridional velocity v hat. Note, however, that the coefficients are not constant in this case, and in fact have a y squared term appears here within the square brackets on the right hand side. This is a more complicated equation than the ones that we've looked at before, and does not have simple wave-like solutions associated with it. In order to solve for the meridional dependency of v hat, hence, we'll have to examine this differential equation in a bit more detail. So let's look at two asymptotic limits, which will allow us to simplify the form of this differential equation. First of all, we're going to look at the case where h goes to infinity, and we're going to look at the case where beta is equal to 0. So in the asymptotic limit as capital H goes to infinity, this corresponds to non-divergent motion as a consequence of the continuity equation. Since the continuity equation shows that the horizontal divergence of the perturbations is equal to minus 1 over gh times the partial derivative with respect to time of the geopotential perturbation. Then as h goes to infinity, the right-hand side of this quantity goes to 0, and so we have that the flow becomes non-divergent in this limit. Then the equation number 8 reduces to the form shown here, given as equation number 9. Note that equation number 9 does have constant coefficients associated with it, and hence will have wave-like behavior. So in the asymptotic limit as h goes to infinity, we obtain this equation. We can then assume an amplitude function for v hat, which is wave-like in nature. That is, v hat equals v naught times e to the ILY. And this provides us then with a frequency nu, which actually satisfies the Rossby wave dispersion relationship. So these are actually an example of Rossby waves in the equatorial system and are known as equatorial Rossby waves. These waves also have character analogous to those that we've seen for Rossby waves, including westward propagation relative to the mean flow. In the asymptotic limit as beta equals 0, the influence of rotation is eliminated. Then due to linearity, solutions exist in an analogous form, however with a different coefficient. Equation 8 then reduces to a shallow water gravity model with the coefficient shown here, and non-trivial solutions then exist if the frequency satisfies plus or minus gh times kappa squared. This is actually a pure gravity wave response. That is, all waves propagate at a phase speed of square root of gh, where square root of gh is constant, and it corresponds to gravity waves along the ocean surface. So this includes both eastward and westward propagation of waves. So in the general case, we need to take into account that the general solution must satisfy these asymptotic limits. So we seek solutions of the meridional distribution v hat with the boundary condition that v hat has to go to 0 as the y coordinate goes to infinity. That is, we don't want these waves to grow without bound. For small y, we need to have that the quantity within square brackets is positive and solutions oscillate in y. And for large y, the coefficient is negative, so solutions must either grow or decay. This is very much analogous to the behavior of the wave equation and the corresponding exponential equation with both growing and decaying roots, which we've seen previously in this class. Note that only the decaying solution will then satisfy the boundary condition. So Matsuno in 1966 actually showed that decaying solutions only exist if the constant part of the coefficient in square brackets satisfies the relationship shown here. That is, it needs to have integer values, and in particular odd integer values, in order to have decaying solutions away from the equator. So this greatly limits the number of possible solutions that could arise from this differential equation. This is actually a cubic dispersion relation then for the frequency nu, where we have a new free parameter n associated with the system. It actually determines the allowed frequencies associated with a particular zonal wave number k and meridional wave number n. So for a particular zonal wave number, one then gets a family of solutions which have different oscillation frequency in the meridional direction. So in 8, if we replace y by the non-dimensional meridional coordinate c given here, then we actually obtain that there is a closed form version of the solution in terms of Hermite polynomials, as shown here. The Hermite polynomials are a special set of polynomial functions which arise from mathematics and appear as solutions of this differential equation. The general solution will then have the form v hat as a function of c is equal to v naught for constant v naught times the Hermite polynomial as a function of c times e to the minus c squared over 2. Here the first 3 examples of Hermite polynomials are shown. Depicting these Hermite polynomials in space, one obtains solutions that look like those depicted here. Here from left to right, we see Hermite polynomials with coefficients n equals 0, 1, 2, 5, and 10. As you can see, the value n associated with the Hermite polynomial actually corresponds to the number of roots. That is the number of times that the Hermite polynomial passes through 0. So for n equals 1, it has 1 root located exactly at the origin. For n equals 2, it has 2 roots symmetric about the origin. For odd values of n, it'll always have a root at 0, as well as roots away from the equator. And for even values of n, it will not have a root at 10, but will still be symmetric about the equator. Hermite polynomials are obtained in general from the functional expansion shown here. So in general, there are 3 solutions for the frequency for this algebraic system. These can be interpreted as 3 types of waves. namely an equatorial trapped eastward moving inertia gravity wave, a westward moving inertia gravity wave, and a westward moving equatorial Rossby wave. Note that it's characteristic of Rossby waves in general that they are westward propagating with respect to the mean flow, and so there are no eastward propagating Rossby waves that arise from this solution. However, one should take into account that there are eastward solutions of the shallow water equations in general, and those are the equatorial Kelvin waves that we discussed earlier. For the case that n equals 0, we have a special case actually. For n equals 0, the meridional velocity perturbation has a Gaussian distribution centered about the equator. And so this leads to a particular special case. The dispersion relation in this case factors as seen below. There are then three roots associated with this system. We have a root arising from the right-hand side of the expansion, which is equal to minus k square root of gh. But recall from earlier that in order to eliminate phi hat from the equations of motion, we had to divide through by nu squared minus k squared gh. So this solution actually leads to a zero denominator for that component of the equations, and hence is not physically permittable. So only two roots then exist for the case n equals 0, and these are given below. So the positive root that arises in this case corresponds to an eastward moving equatorial inertia gravity wave. The negative root, on the other hand, corresponds to a westward moving wave, which resembles an equatorial inertia gravity wave for long zonal scale, that is for k approaching 0, and an equatorial Rossby wave for zonal scales that are characteristic of synoptic scale disturbances. So typically on the order of wavelengths of 1,000 kilometers or so. So this wave is exotic in some sense. It's a very unique wave that appears and is a westward moving wave called a mixed Rossby-gravity wave. Mixed Rossby-gravity waves kind of have the behavior which is shown here. They're asymmetric about the equator, hence exhibiting high pressure to the north and low pressure to the south, or vice versa, as well as meridional velocities which are non-zero at the equator. The zonal velocities are positive around the high pressure region and negative around the low pressure region. These waves then propagate westward relative to the flow.